Quantum mechanics is the set of rules that run the universe when things get very, very small. At this scale, the world stops behaving like solid objects and starts behaving like probability. Classical physics is a map for big things. Quantum physics is the map underneath the map. And the first strange truth is this: the universe does not always pick one outcome. Sometimes matter behaves like a particle. Sometimes it behaves like a wave. Often, it behaves like both. If that sounds mystical, it's not. It's precise, and it's unbelievably powerful. In the quantum world, a system is described by a state, like a recipe for what could happen. That state is often drawn as a wave function, a mathematical object whose shape encodes probabilities. The taller the wave at an outcome, the more likely that outcome is if you measure. But measurement is not passive. To measure is to interact, and interaction forces a result. To result, the system doesn't stay frozen. It evolves again, following the Schrödinger equation. It's deterministic math, until the moment you ask for a definite answer. Quantum mechanics has two faces: smooth evolution and sudden outcomes. That split is the source of many debates, but the predictions are astonishingly accurate. Superposition means a system can be in a combination of states at once.
Not half and half like confusion, more like waves adding with other waves.
A particle can take multiple paths until you force it to reveal which one. The double slit experiment shows this. Waves from two slits interfere. Where waves add, you get bright bands. Where they cancel, you get dark ones. But if you watch which slit it uses, the interference pattern disappears. Active learning which path changes what happens. In quantum physics, information is physical. Knowing is an interaction. Remove the interaction, and the wave behavior comes back.
So the quantum world is not either or. It's a deeper rule that includes both.
Then there's the uncertainty principle. Some pairs of properties can't both be sharp. The more precisely you know position, the less precisely you can know momentum. This isn't a flaw in your instruments. It's built into quantum states. Quantum also means quantized. Certain values come in steps, not a smooth slide. Atoms emit specific colors because electrons change energy in specific chunks. Pile up enough quanta and the steps blur until the classical world emerges. Now we reach the strangest feature: entanglement. Shared quantum states between distant objects. Entangled particles don't carry separate instructions. They share one combined description. Measure 1, and the shared state updates. The outcomes are correlated beyond classical limits. This looks like faster-than-light influence, but it cannot send usable information faster than light. You can't control the result you get. You only discover how the pair matches. Bell tests violate classical bounds, ruling out a large class of local hidden variable explanations. Entanglement is a resource, like fuel, but for information processing. With entanglement and classical communication, you can teleport a quantum state without moving matter.
This is the dream behind quantum networks, distributing entanglement across distance.
But before we talk about the future, we need to face the measurement problem. Quantum states are fragile. The environment constantly tries to measure them for you. This is decoherence. Delicate quantum phases leak away into the environment. Information spreads out. And once it spreads, interference becomes impossible to recover. This is why Schrödinger's cat is a paradox. Superposition meets a noisy world. In practice, decoherence makes macroscopic superpositions vanish almost instantly.
But the equations never say exactly when measurement happens, or what counts as an observer.
Where do you draw the line between the quantum system and the classical observer? Different interpretations answer differently, without changing predictions. Some say the wave function is just a tool. Some say it's real. Some say reality splits. And quantum mechanics keeps working, whether you see it as physics, information, or something deeper. So what is quantum mechanics, really? Let's map the leading hypotheses. Not to pick a winner, but to understand the landscape. Copenhagen-style views treat the wave function as a predictive tool. Measurement updates what you can say. Any world suggests the wave never collapses. Instead, outcomes branch into non-interacting histories. Pilot wave theories keep particles definite, guided by a real wave. Non-locality is built in.
Collapse models propose the wave sometimes collapses spontaneously, rarely for small things, often for big ones.
Information-based views treat quantum probabilities as expectations about experiences, not properties alone. Relational ideas say quantum states are relative to an interaction. Facts are about relationships. There is no universal agreement on interpretation, but the theory's power does not depend on settling it. Because whatever the wave function is, we can harness its rules. And that brings us to the modern promise: quantum technologies. But first, why quantum is so hard to build?
A qubit is a controllable quantum system. Its power comes from superposition and entanglement.
Quantum gates rotate states and create entanglement. Computation becomes controlled interference. The goal is to amplify the probability of the right answer while canceling wrong ones. Some algorithms can outperform classical ones for specific tasks: factoring, search, and simulations. A natural use is simulating quantum chemistry, materials, catalysts, batteries, maybe new medicines. The obstacle is noise. Qubits decohere. Gates have errors. Long computations break.
Quantum error correction fights this by spreading information across many physical qubits into one logical qubit.
You measure error syndromes, not the information itself, so you can correct without destroying the state. If hardware errors are low enough, bigger codes can suppress logical errors dramatically. Teams are pushing towards scalable, error-corrected machines, where one reliable logical qubit becomes many. Today's devices are noisy. The long-term goal is fault-tolerant quantum computing. Quantum computers won't replace classical ones. They'll become specialized tools for problems that match quantum structure.
One famous impact is cryptography. large, fault-tolerant quantum computers could break some public key schemes.
That's why the world is moving toward post-quantum cryptography, new standards designed to resist quantum attacks.
Quantum key distribution is another approach, using quantum states to detect eavesdropping during key exchange.
Experiments have used satellites to distribute quantum keys over huge distances, using photons in space. A future quantum internet would distribute entanglement for secure links, clocks, and distributed sensing. But the most immediate quantum revolution may arrive through sensing, quiet, precise, and everywhere. Quantum systems make exquisite sensors, atomic clocks, magnetometers, accelerometers, and interferometers. They can detect tiny magnetic fields, map brain signals, and measure gravity with extreme precision. In principle, they can enable navigation without satellites and measurements that classical devices struggle to reach.
Quantum effects also drive new materials, superconductors, topological phases, and devices built from quantum structure.
As computation improves, quantum simulation may help design molecules and medicines more efficiently. So quantum mechanics is not just weirdness, it's leverage over reality's deepest rules. If civilization masters error-corrected quantum systems, we gain new tools for chemistry, optimization, and communication. But progress will be uneven. Engineering is hard. Timelines are uncertain. Hype can outrun hardware. Quantum mechanics teaches a quiet lesson. The world is not obliged to match our intuition. Under the surface of certainty is a sea of possibilities, shaped by rules we can learn, but not fully control. The meaning isn't that reality is random. It's that attention matters, because outcomes are born from interaction. Quantum mechanics is the most accurate theory we've ever built, and we still argue about what it is. Maybe that's the point. The deepest truths are not only answers, but better questions. If you want calm science with a sense of wonder, tap like and subscribe to Arcane Knowledge.